So this is the third of 4 videos on predicting products of chemical reactions, and so we're going to look at the third type, which is a single displacement reaction, sometimes called a single replacement reaction. So let's take a look at this reaction for a minute here. So the general formula is A plus BC goes to make B plus AC. And so what's really going on here? What does it appear that is happening? And so this reaction type is often called a single replacement because what we see is element A replacing element B in the reaction. So it's almost as though B is kind of like being bumped out by A. A is just kind of going in there, knocking B out of the way. B is by itself, and now we have the compound AC. So how are we going to recognize that we have a single displacement reaction? Well, what you're going to see is you're going to see an element reacting with a compound. That's going to be your cue. Okay, that's what's going to let you know that this is in fact a single displacement reaction. Now I should mention too that you may see the reactants written like BC plus A. So it's kind of like saying it goes to make, and it's kind of like saying, well, I know that 2 plus 3 is the same as 3 plus 2. So the order in which we put these reactants doesn't really matter. It will mean the same thing. What you're looking for is element and compound combination. So let's try a couple of examples. Now, before we go any further, I need to explain to you this thing called the activity series. And so the activity series is kind of a bit of a hierarchy of elements, right? It describes which elements are more powerful than others. So for instance, lithium is here at the top because it is the most powerful element in terms of its ability to bump out another element. So, it gives us a hierarchy or an order of dominance, if you will. So for example, gold is the least dominant element on our activity series, which means that it can't bump out anything. So for instance, let me give you an example here. Our general formula is A plus BC goes to make AC plus B, right? And so here we see that A is bumping out B, but A can only bump out B if A is higher on the list, if it has dominance over B. Okay, so if you're not sure about what I mean, let's go through a couple of examples and I'll help you see that. So in this first example down here, we see, so this is where I am right now, we see an element zinc, and we see a compound hydrogen chloride or hydrochloric acid. And so we can tell that this is a single displacement reaction because I have that element and a compound combination. And so, because I know that I'm going to be making a compound and an element, this is where I'm going to have to use my crossover rule. And so this is usually where I start. I will take each of the elements that are involved, whether they be on their own or in a compound, and I just write out their ionic charges. So I would say, okay, zinc on the periodic table has a 2+ charge. And remember, those charges are written in the upper right-hand corner for you to refer to. Hydrogen has a charge of +1, and chlorine has a charge, chloride, the chloride ion, it has a charge of -1. And so really, if this is going to happen, if zinc can actually bump out hydrogen, then zinc needs to be dominant over hydrogen. It needs to be higher on our activity series. And so let's go over to our activity series and find each of these, zinc and hydrogen. So I can see that zinc is in fact higher than hydrogen. So that means that zinc can bump hydrogen out of the way. And so it's going to do that. So what happens as a result is my zinc ion is going to combine with my chloride ion. And another way to remember what's going with what is opposite charges attract, right? So my positive zinc is going to want to go with my negative chlorine. They're going to be attracted to each other. My zinc is never going to want to go with hydrogen because they have like charges and they will repel each other. So then I simply do my crossover rule with these two substances, right? So I have zinc with a 2+ charge and chlorine with a -1 charge. That crossover is going to give me zinc chloride. And then I'm stuck with this hydrogen ion on its own. But remember, hydrogen can never exist on its own. It's going to always be part of my diatomic list, and I'm going to write it as H2. Okay, so that's how I go about doing this question. Now, all of this business here on the side, this is all sort of on the side thinking stuff. That's how I would show my work. But here is my solution to this question. Okay, so let's try a second example here together, just to get us used to this process. And so when I look at this question, I can see right off the bat that I have a single displacement reaction because I have tin, which is an element, and this sodium nitrate, which is a compound. And so if this reaction is going to proceed, then my tin needs to be able to bump out sodium, right? That needs to be able to happen. So let's go refer to our activity series and find tin, and let's find sodium. Okay, and so I see that tin is right here, and I see that sodium is right up here. So in this case, you know, tin is below sodium. It ranks lower in the hierarchy of elements, and so tin does not have the strength to pull sodium away from that nitrate. And so in this case, what we would say is no reaction. This reaction can't happen because tin is not powerful enough to bump out sodium. And that's it. Okay, let's look at another question. Okay, so I would like for you to give this question a go on your own and see if you can predict the products effectively. You're going to get the most out of this if you're trying the questions and then kind of seeing if you got it right, and if you got it wrong, you'll learn more and that will kind of stick in your brain. Okay, I'm going to take up this question now. And so again, I'm just looking for those cues that this is a single displacement reaction, and I can see element and compound, so I'm good to go. And so if this reaction is going to happen, I know that lithium is going to be bumping out the other metal, sodium. And so I need to look to see that order of dominance. For me, as soon as I see lithium, I know lithium's at the top of my list, and everything else ranks lower than it. So I know lithium's going to be able to bump out sodium. But you will have this list with you, and so you'll be able to kind of see that even if you didn't remember that bit about lithium. Okay, and so here's my side work. So my side work is that lithium has a charge of +1. Sodium has a charge of +1. And bromine has a charge of -1. And so remember that we're going to end up with lithium bumping out sodium. And so sodium I can simply write here as being on its own. And it's not part of my diatomic list, and so sodium's just going to be there kind of just by itself. And then what I need to do with the remaining elements, right, lithium and bromine. And remember, lithium's going to want to go with bromine because they have opposite charges and they will attract each other. So when I do my crossover rule with these guys, I have +1 and I have -1. And those charges will cross over to just cancel each other out. That tells me the ratio of lithium to bromine in this compound has to be 1:1. And finally, I get LiBr. And that is it. Okay, now it's just a coincidence, right, based on charges, that I don't have any subscripts in these products. So just be aware of that. And let's try another example. So this example looks a little bit more complicated. What I'm noticing here first, right off the bat, is that there is a polyatomic ion. So this is a time and place for you to maybe pull out that polyatomic ion chart before giving this question a go. And then when you're ready, resume the video. Okay, so again, looking for those cues that this is single displacement, I have element and compound. And so my first instinct is to go ahead and look at our chart. And so I'm finding potassium. Potassium is up here at the top, and then aluminum is below it, which means in fact that, you know, potassium is going to be able to bump out our aluminum cation out of the way. And so what I'm going to do is I'm just going to down here write out all the ionic forms of each element. So potassium, I've got aluminum, and I've got this sulfate ion, SO4. And now I'm going to write out all their charges. So +1, aluminum is +3, and sulfate is -2. And again, this, the sulfate you're getting from that chart with the polyatomic ions. Okay, so in this case, I know that potassium is bumping out aluminum, so it's going to bump out aluminum and go with the sulfate, right? And again, those ionic charges being opposite are telling me what is going together here. And so let's just do that crossover rule with these. So I have potassium with a +1, and I have sulfate with a -2. And you'll remember that when we talked about forming these compounds, we put brackets around the polyatomic ion and then did our crossover. And what we get when we do that is K, and then this 2 over here comes down, and then bracket SO4, bracket 1. And now I see that, there's a 1 outside here, and so that means that, when I multiply 1 by anything inside of brackets, it's not going to change that thing inside the brackets. And so in this case, I can simply write this as K2SO4, and I'm done. So I'm going to do that. I'm going to write that as my answer here, K2SO4. But then I have aluminum left over, and aluminum is not part of those diatomic molecules. It's not on the list for Hofbrinkel. And so I can simply just write out Al. And I'm done. And so there's a few things I can do here if I wanted to balance this question out, right? So I'm going to go ahead and do that. And maybe if you want to, pause the video and give that a try. So I'm seeing that I have three sulfates. So I'm going to put a 3 in front of my potassium sulfate on the product side. And that's going to give me 3 times 2 potassiums, so 6 potassiums, so a 6 over here. And then I see that I have 2 aluminums on my reactant side, so I'm going to put a 2 in front of my aluminum. And that is it. Okay, we've got one more example to show you, which is one where students often mess up. So I'm going to just kind of provide a bit of an explanation for it. Let's take a look. All right, so in the case of sodium and water. So sodium and water are a really explosive reaction. Normally in class we would look at this and see how reactive this is. Let's see how it's reacting. So one thing that's really important to know about our water and how water chooses to ionize, and this is just what it does, okay? Now, students will often say, oh, well, I have H plus and O2 minus, right? The charges on these elements, but I'm here to tell you that, that is not how water chooses to ionize. So this is a bit of a memory piece, okay? Water actually chooses to ionize to form an H plus ion and that hydroxide ion that we see in our polyatomic ion chart. Okay, so that's just something to commit to memory, right? So, get to know this. All right, so then we have sodium. And so looking on your periodic table, you should be able to see that sodium has a +1 charge. And so now what we're going to do is we're simply going to perform our crossover rule as we have before. So positive sodium is going to want to go with negative hydroxide. So let me go ahead and write these down here. So I have sodium with a +1 charge, hydroxide with a -1 charge, putting those brackets around our polyatomic ion. In this case, we don't really need to because the charges are 1 and 1, but it's just a good habit forming piece. So that will give me sodium hydroxide. So I'm going to put that in as my first compound. And then so what is left? Well, I have this hydrogen ion, and I just simply need to remember that hydrogen is part of that group of diatomic elements and Hofbrinkel, and I'm just going to write out it as H2. Okay, and so, that this is an interesting piece because, in class normally I would do this reaction. We would see, oh, here's some water, and then I would take my chunk of sodium and I would put it in there, and what would happen is I would see these bubbles of hydrogen gas forming, and, you may remember from grade 9 that hydrogen gas is explosive, and so if I collected this gas here and then lit it on fire, I would hear a nice loud pop. Okay. So that was the last example from our single displacement reactions. Just remember the activity series you will have to use on any quizzes in this section. And please reach out if you have any questions.